Yes, Kashinath, am I audible?
Yes, sir.
Okay, screen is visible to you, no?
Yes, sir. It's visible.
Okay, thank you. So yesterday we discussed about thermal analysis of the concentrating collectors. So useful heat gain. So the changes in the useful heat gain equation you have seen, where you have to take the overall loss quotient by concentration ratio. So apart from this, remaining equation remain same as per the flat plate collectors. So that we have seen. And the different losses to explain, I have taken this sketch. So apart from the equations, you have to just observe how the energy is going to be lost from this any type of concentrating collector that we have seen the yesterday's class. So the energy received from the sun is reflected back to the absorber. Okay. So area of the absorber surface area or the cross section area to the receiver area. So that is the concentration ratio. So depending upon that, we are going to focus the solar energy to the receiver. So it may be a point or line focusing or a different type of focusing the collector. And in this, you can see the optical losses will be there. Then radiative or convective losses from the receiver will be there. Also, some heat loss will be there with the different accessories of the receiver system. So like this, we have seen the losses with respect to solar concentrated collectors and the useful heat gain, how much is possible from the concentrating collector with respect to concentration ratio. How much is the concentration ratio we are increasing, that much of useful heat gain will be high. So that we have seen in the last class. Now today we'll try to discuss how to convert this flat plate collector as a concentrating collector also. So this already we have discussed some points in the earlier classes. Now here you can see a flat plate collector is taken here at the bottom. So this bottom line is a flat plate collector which is shown here with some tilt angle beta that we have seen earlier. That's the tilt angle beta. So this tilt angle is the with respect to horizontal surface on the earth. This flat plate collector is always tilted towards some direction because from east to west, whatever the sun path is there, this tilted angle will be towards south. If the flat plate filter is kept in the northern hemisphere, if it is kept in the southern hemisphere, it will be tilted towards northern hemisphere. So like that, the tilt angle will be decided depending upon the solar sun path. So that angle is decided here. Then left is whatever the earlier flat plate collector you have seen, only the normal solar radiation is absorbed by the flat plate collector and absorber plate. But here we are going to increase the solar radiation absorption quantity by applying these reflecting plates. Okay, so these reflector plates you can see here. One is on the south side, one is on the north side, like this you can put for a number of flat plate collectors. If you take only one flat plate collector, what you can do is on all the four sides you can put the reflector plates. But the problem with all the four sides reflecting plates in the east and west side in the solar part, the time is what is available for absorbing the solar radiation will be very less because the shading effect will be more if the reflector plates are towards east or towards west side. So to overcome that shadowing or the reduce the time solar radiation absorption, so what this thought is only to keep the north facing or the south facing reflectors. And some of the reflections may be possible from the ground also. Okay, so that is taken in different case. So to keep in this fashion, so whatever angle required to keep these reflectors in a given position so that in throughout the day, maximum solar radiation can be focused on the flat plate filter. That may be possible. Or you can keep a tracking system so that it will track the reflecting radiations depending upon the solar path. So that tracking of reflectors as well as flat plate filter is very difficult. So that you can decide one of the angle for a given solar path. You can decide one of the angle for a given position also, where this meridian or on the meridian where this position of the flat plate is kept above equator or below the equator of the earth or depending on the different locations. On that basis, you are going to find this angle psi. So psi defines the angle between the horizontal surface of the earth or assumed horizontal surface of the Earth with reflector surface. So that angle is denoted by psi. Now, by applying these extra reflectors, what we are going to do is we are going to improve this working temperatures of the flat plate filters. So earlier we discussed about only the flat plate filters without any uh, concentrating collectors or the reflectors. There we discussed about only up to 80 degrees centigrade or the 70 degrees centigrade of water is heated or temperature is available. But applying these reflectors, extra reflectors aside or just beside the flat plate filter, we can go up to 140 degrees centigrade. This is one of the advantages. So now this flat plate fluid is converted into concentrating collector. Now to find that angle psi, the equation psi is derived under assumptions. So some assumptions are made here. That is, reflector mirrors are adjusted in such a way that sun's rays striking the top edge of the mirror at 12 noon here. Now, all the solar radiations you see are normal to the horizontal surface. So they have assumed that exactly at 12 hours, this angle is decided. So this angle we are finding, keeping in mind that at 12 hours, what is the maximum solar radiation which can focus on the flat plate collector using reflectors. Okay, so that they have assumed and they have calculated this side. So that all radiations are reflected to the top edge of the collectors. So here you can see that from top edge, from this end to this end, all the solar radiations to be reflected back to the flat plate collector. So in such way, we are going to find out this angle and that is kept constant. If tracking system is there, there is no need to continuously find out the psi angle. You can keep one range of angles and automatically by programming the tracking system or by keeping some mechanism, one can trace this flat plate collector or this reflectors all combined during the sunrise and the sunset. So until that they can track the solar radiations so that maximum temperature as well as maximum solar radiation can fall on the flat plate collector. So after finding that with these assumptions, we found out that this psi angle depends on this factor. That is phi minus beta, that is tilt angle, minus 2 phi. So already you know all the angles of the filter surfaces. So I'll not recall once again here. You can just note down that is phi minus beta minus 2 phi plus 2 delta divided by 3. After applying these assumptions with this angle and keeping this tilt angle in the uh, consideration, so they found out that the psi depends on depending on the angle they are talking about. That's why they have taken phi. So phi minus that is 180 minus 180. What is how much is the minus? So total 180 is horizontal line minus beta. So some angle is because of beta. Then another angles are what? Latitude angles and declination angles. So that we are going to find out by phi minus beta minus 2 phi plus 2 delta whole divided by 3. Once you apply this equation or it tells the angle at 12 hours noon. At exactly noon, when the sun rays are vertically falling on the horizontal plane, at that time, what angle should be maintained so that maximum absorption is possible? Okay. So these reflectors are more effective in augmenting or increasing the solar radiations, okay, considering the beam radiations. So here we have not considered actually the diffuse radiations. Diffuse radiations effect will be very less compared to the beam. Okay, next is so this is all about converting a flat plate collector with a to a concentrating collector or with using plane reflectors we can improve the efficiency of the flat collectors. Next last part in this chapter that is cylindrical or concentrating collector. The last part in this chapter is about cylindrical parabolic collectors and its materials and its working procedure. Already we have studied in second chapter, so again we are repetition of this and important is the material. So that we have to focus on this part. And the next chapter is in this last module is solar economics. And just recall the syllabus here once again. What all things we have discussed in this chapter. So going back to syllabus of solar energy, you can observe here syllabus. In the syllabus, we have discussed general characteristics, definition of terms. Yesterday we have discussed all those things: concentration ratio, intercept factor, acceptance angle, methods of classification and types. We have discussed in the first class of this chapter. Then types of concentrating collectors and their thermal analysis. Thermal analysis yesterday we have done with considering concentration ratio. Now today we have discussed flat-plate collectors with plane reflectors. So that I have discussed now. Just now. Now left is cylindrical parabolic collectors. So on this we need to discuss some theory. So in this chapter, only the thermal analysis of this concentrating collector is told, but thermal analysis is nothing but the equations. And next is for numerical, we have not mentioned anything about the going for the analysis of cylindrical parabolic collectors, because this is the first type of concentrating collectors. But here what they are told, types of collectors with thermal analysis. That I have to consider here. This is the thermal analysis of the simple concentrating collectors. But which type of collectors is not mentioned. So later what we have to do is, last part what we have to discuss is theory part of this cylindrical parabolic collectors. So to just understand some heat transfer with respect to this concentrated collector, I have taken an equation. So that will complete today. And from next week, probably we can start with economics analysis of solar systems. Okay. So this is about the last module, fifth module, what we have discussed. Okay. Now coming back to the next part, cylindrical parabolic collector. So whenever this term comes, all of you can remember that it is having a cylindrical body. You can see the cylindrical body like a pipe, cut section of the pipe, like this body here. And it is a parabolic. So this, whatever the cut section is there, this is not exactly circular. It is a parabolic shape. Sometimes it may be circular also. Sometimes to increase the concentration ratio, it may be parabolic shape. Okay, so name that, they have named it as parabolic cylindrical collector, or it may be cylindrical parabolic collector. You can just observe this sketch, everyone can understand. So at the focus of the focal axis, so here it is having axis because it is a cylindrical surface is there as a reflector. So reflective coating or mirrors are used here, so that all the solar radiations, the aperture area, are entering on the surface, reflector surface, and all the radiations will be focused on this central axis or the focal axis. You can call focal axis. The absorber tube located at the focal axis. The tube should be kept at the focal axis such that the absorber cover, through the absorber cover, transparent cover, the solar radiations can be focused on this tube. So that tube is made up of metal. Okay, so on that it will be focused. Then whatever the fluid is passing here, fluid in is there, so some fluid is coming inside and some fluid is going outside. So these fluids are maybe used for some chemical processing or industrial high temperature applications, or it may be for the simple power plants. Okay. If it is a paraboloidal shape, you can go for power plants, but here it will be less than that. Temperature will be less than that. It is up to 120 degrees. Temperature is up to 120. Sorry, it is up to around. You can get I think 200 degrees centigrade maximum. 200 to 250 degrees centigrade. So here concentration ratio what is maintained is up to 80, 10 to 80 can maintain. And this angle, rim angle is measured. So whatever the rim angle is maintained here, it is measured from this line. So the line is drawn here, half of the hemisphere, from there to this line, or to this tip of the collector. So this angle, now it is in the sketch, it is shown around 90 degrees, but it may be from 70 to 120 degrees, so that concentration ratio can be improved. That's it. So now whatever fluid is entering, it will absorb all the heat once it is flowing from this into this end, so that high temperature fluid can be taken out for the applications. And to have the tracking system, it can have the movement about these points, or completely this trough itself is rotated at a given angle for a given time. And this is the axis of rotation. Okay, at this point, you have to go to the aperture or the complete system. go through this sketch once again for a minute. So here nothing much is different from the earlier discussions. Same thing, it is repeated here. Now we'll see the importance and materials used in this type of connectors. So that is cylindrical parabolic connectors. So in the syllabus, they are not mentioning paraboloid. If it's paraboloid, the concentration ratio is also very high, and also the applications of the temperature, range of temperature of this paraboloidal shape is also very high compared to this cylindrical type. The absorber tube is usually made up of steel, copper, or aluminum. It's coated with a heat resistance black paints. So now, coating material already we have discussed in the flat plate case, so that only we can record here. And also, the paints are not preferred. Actually, the paints are not preferred as a coating surfaces. Okay. So maybe to avoid the losses from the surfaces, black paint you can use other than the different color paints. So black paint can be used, not exactly the various colors of paints. So one of the paint is black paint. So it can be used as a selective coating or with different chemicals. So it is generally surrounded by a concentric glass cover. So what is concentric glass cover? It's fluid pipe what you are seeing. The fluid pipe is made up of metal. Above this, there is a transparent cover, transparent tubing is it. With a long pipe, a concentric to the metal pipe, there is a transparent glass tube or a plastic tube is there to its entire length. It may be one or two, so depending upon our losses or dust collection or requirement, we can go for one or two maximum glass cover, as like in flat plate coating or before. So that is separated. The glass cover as well as the metal plate is separated by 1 or 2 centimeters with some evacuation if possible, so that performance can be increased. Okay. The liquid heated in the collector depends upon the temperature required. If the temperature required is high, then the flow rate should be very less. If the temperature required is very less, then you can neglect the tracking system or you can increase the flow rate inside the tube so that the temperature absorbed or heat absorbed by the tube will be less. So that all depends on the concentration ratio, aperture area, and the receiver area. Also, with respect to focusing, the solar radiation towards the aperture area, or you can go by increasing or decreasing the flow rate of the fluids. So by that, one can control the temperature. And these fluids used are maybe organic liquids or some special oils, oil also can use, so that you go for water or some low temperature liquids, low vaporization temperature liquids, then controlling this temperature and the phase is very difficult in the fluid. So that to keep the fluids in a given phase with some sensible heat, to control the fluid movement with some required pumps to go for an active system. So in such conditions, the liquid what is used in the heating of the pipes that we use, it should not convert its phase, not change the phases continuously. So that will become very difficult to pump the fluid inside the pipe flow. So in such conditions, we can go for special valves such that in given range of temperature, it should not vaporize and it should not convert directly to the liquid. Okay? So these liquids can yield very low heat transfer coefficients or loss coefficients, such liquids can be used. Then reflecting surface is generally called back silver glass. So what are the reflecting surface is made here? At the back side, to reflect the solar radiation, it is silver color or some chemicals are also used. So that is discussed in this point. The back side, it will be silver or any some coating is done on the back side. And it is fixed on a lightweight structure because tracking system should not be really weight. It should be very light and it should be very stiff also. It should not break easily. So nowadays many times glasses are reduced because glasses are having very low stiffness or breaking is more for the glasses. So in case of glasses, they are going for metals with back coating so that some reflection is possible. And life is also long, cost can reduce. Okay, so usually made up of aluminum sections with that structure so that light weight can be achieved. So some more details of materials if you see. The reflecting surfaces are made up of glass or like plastic films you can go for and polished aluminum surfaces. So this can also have a very good reflecting surface and the glass can have 95% reflectivity. Such type of glasses you have to choose. Whereas aluminum reflectivity can be achieved up to 85%. So this is a very good option. Like aluminum reflectivity to see. Aluminum is having very good life. Cleaning is also very simple. And surfaces is very simple for us compared to the glass surfaces. So one can think of aluminum surfaces with some coating at the backside so that reflection can be improved. Or backside coating is required for the metals because the heat cannot be lost also. So some heat as well as reflection can be concentrated inside that reflector as well as absorber. The types of glasses available are
Excuse, excuse me, sir.
yes,
Sir, where these aluminum reflectors are used? Applications like glasses are more 95% reflectivity. Even though aluminum they are using means applications of aluminum reflective material.
your voice is not clear. Application of aluminum is required.
Ah, yes, sir. Yes, sir.
Application of aluminum is
Application of
like
aluminum.
just a minute. Yes, aluminum applications you want, no? Huh.
Yes, sir. Yes, sir.
Aluminum, as discussed here, it can be used for multiple purposes. One is for preparing the tube. This tube, what you are seeing here, of the fluid. For that also you can use aluminum. And to make the complete system lightweight, this all connectivity between the reflector and absorber, the tube, and the complete structure of this cylindrical parabolic system, and the support system, with connector supports what you see. So entire system can be made up of aluminum. And nowadays also, in place of glasses, what they have mentioned here is, in place of glass, so that maintenance and handling of this glass is very difficult. So to overcome that, one can go for aluminum surfaces, which is polished aluminum surfaces. So as you can see outside, some steel surfaces can give some reflections. You might have seen, or some metal surfaces with some polished or clean surfaces. You can see some little reflections. So that's why the aluminum surface, if you use for reflection quantity is very less compared to glass because you cannot overcome the mirror effect of the reflection of the glasses up to 95%, very good. Only 5% some losses will be there. But if you go for aluminum, handling, weight, cost is very less compared to glasses. And maintenance and other things will be very simple for us. But the reflectivity is very less. But to overcome the initial cost, okay, and other things like handling or maintenance and the production also. Production of aluminum surface is very easy for us. So in such cases, we can compromise with the reflecting abilities. So like that, this aluminum is having very much application in this solar systems. Did I answer your question?
Okay, sir. Yes, sir. Yes,
Okay.
sir. Got it.
So to come to glasses, see these things are also applicable for our flat-plate filter also. But here I'm talking about reflecting surfaces. Reflecting surface is not using flat-plate filter. It is using only these concentrated filters. Okay, now coming to the other parts. So other parts can be common for flat-plate filter or concentrated filter. So that is one is glasses. So glasses used are soda lime glass, lead alkaline. You can just check in online what type of glasses these are. And next we have the borosilicate glass, what you have observed in our chemistry lab or some other experiments. You might have seen the borosilicate glass on books. So why we have taken only these type of glasses because these are having very good reflectivity, and also if you go for the keeping on the cover, absorber cover, absorber cover quantity, there also I can go for such type of glasses which are having high transmissivity, okay, and good reflection. If you go for backside coating, front side it can have a good reflection also. So in such applications, we can go for such type of transparent glasses or very clean glasses. Soda lime, lead alkali, borosilicate, and aluminum silicate. Okay, so these are the good glasses we can go for. Then silver coating is also used on second surface, means backside surface of the glass to make it as a mirror. Then reflecting surfaces used for Fresnel lens, what I told, are generally made of plastics. So that Fresnel lens, if you see, the surface roughness will be there. Any spectral base you can see. Otherwise, you can like this. See here, this is the Fresnel lens. Fresnel lens is trying to convert all the solar radiations towards a focal point. And other side, if you see the Fresnel lens, it is having some rough surface here. It's some given proper angles. Okay, so the thickness of the Fresnel lens, it is continuously changing here in a zigzag pattern. So for this, if you go for glasses, manufacturing of Fresnel lens is very difficult. In such conditions, one can go for plastic materials that having good transparency, as well as if you go for back coating, it may have some good reflectivity also. So in such conditions, you can go for plastic material like polymethyl methacrylate. Using these plastic materials, one can also build the Fresnel lenses that are of very low cost, and the breaking of these Fresnel lenses are also very less if you go for plastic materials. Okay, and also it is having high resistance to the oxidation. So such type of plastics you have to choose, and you can use it for uh, solar reflectors also. Next is the materials used for the absorber tube. So as I told in flat bed pellets, you can go for steel, aluminum, copper, which are having the high absorptivity and less reflectivity. Or can tell good modulus of elasticity, thermal mass, or yield strength. In such conditions, it will have very good properties to absorb the more heat and to lose very less heat. Such materials we are going to use. So again, depending upon the cost, also you can choose different materials. And also the corrosion resistance. It should have some corrosion resistance to the atmosphere so that some treatment can be done and the life of the system can be improved. The next is the absorber cover. So again, this is made up of glass or plastic you can use. So these absorber covers should have high transmittance to particular wavelengths. This is very important. Why? Because if you choose the plastics or the glass covers with transparent to the ultraviolet radiations, it is very difficult because on our Earth's atmosphere we have maximum solar radiations with a very low wavelengths. In visible region or in the infrared, we have maximum solar radiation. So in such radiations or wavelengths, these glasses or plastic materials will have good transmittance or good transmissibility. So such type of covers can be chosen. Next is the physical properties such as it should have coefficient of expansion or contraction. It should be very smooth or soft in application. Then one or more covers can be used so that it can reduce the losses of the heat that can be done. And advantages of glass cover are more. But actually speaking, if you see the glass covers, initial cost is very high. Handling and maintenance of the glass covers are very difficult compared to the plastics. But advantage of glass cover, as you have seen, is having good reflectivity or very good transmittance compared to the plastic materials. Okay, so this is like a compromise. You can go for plastic or you can go for glasses depending upon our requirements. If you want very good life and low maintenance and good handling, one can go for plastic material. If you always observe on the efficiency, if you want only efficiency rather than handling or maintenance and life, then one can go for glass material. Next is the absorber surface coating. So this also already we have discussed. And just recall from the flat plate collector what absorber coatings or selective coatings we have discussed. Same thing can be done here. Some other absorbing coatings on the backside if you see. So that can be like black paints you can go for, or fused vitreous material or the porcelain materials you can go for. So that non-selective coatings. So this should not be chosen. That I have written here. What should be chosen? I have already discussed in the flat plate collector chapter. So which selective coatings or non-selective coatings should be avoided are: one is paintings, many different paints should be avoided. Then vitreous materials or the porcelain materials should be avoided, or some enamel coatings. So that this will avoid the absorption of the heat. Okay, we should improve the absorption of heat rather than reducing the heat as well. Then fluid carrying the heat from the absorber. So these fluids will be chosen such a way that it should absorb more heat, okay, and operate at very high temperatures without changing the phases. It should be stable at different temperatures and non-corrosive, and it should be very safe. It should not catch any fire, or it should not reduce its properties at different temperatures. So these all conditions should be properly chosen. So common fluids used are special oils, water at high pressures should operate, and sometimes air also can be used. For any applications with hot air, you can go for the same concentrated collector or a flat plate collector with air as a fluid, or you can go for water or a special oil. If it's very high temperature, you can go for oils to overcome the phase changes. Okay. Next, to just understand in numericals how to understand these losses and useful heat gain, I have taken one simple example. Okay. So here they have taken parabolic concentrating collector. This is not in the syllabus. Parabolic concentrator is not in the syllabus. Just to understand the numerical, I have taken this example. So here they have given parabolic concentrator. Means it is a paraboloid dish like this. Its shape is this paraboloid shape. That concentrator is used to heat a thermo oil. So oil is flowing in the tube. That oil they have to use used for a power plant. So even power plant is also not discussed in the syllabus. Taking the following data, determine the exit temperature of oil when the inlet temperature is 280 degrees centigrade. So inlet temperature of the oil is 280. How much is outlet temperature? Inlet is 100. So on this reflector surface, okay, the solar beam intensity is 750 watts per meter square is fine. Aperture area of the connector is 240 meter square. Aperture area is the circular cross section area. Circular surface area to take, that is the aperture area. That is given 240 meter square. Concentration ratio CR, area of aperture to the area of the absorber, total area of the absorber to C. Ratio is 40. Mass flow rate of the oil is 36 kg per minute. So per minute, 36 kg of oil is flowing. Then Cp of oil 3.2 kilojoules per kg. Specific heat of oil is given. So this always I told you mass flow it is given, Cp is given means mCp delta T will help us to find out the outlet temperature. Very simple. Then ambient temperature is also given 30 degrees centigrade. Heat loss coefficient is given 8 watt per meter square per degree centigrade. Then heat removal factor. This we discussed in the earlier chapter. Whether it is useful or not, we'll see the solution. Heat removal factor is given. This is nothing but the actual heat absorbed by the fluid to the ideal heat absorption. So that is 0.96. That is always less than 1. Then efficiency of the optical system is 75%. Then tilt factor RT is given or RL is given 1. So we'll see the solution. Here we have recalled the full heat gain in terms of heat removal factor. So again, you can recall from the our discussion of flat plate collector, that is with heat removal factor. Using that, how to find out useful heat gain? That is FR into AP. So here directly FR is given. So I am not recalling FR equation. FR into area of the absorber plate into total incident solar radiation into efficiency. Why? Because this is a concentrating collector, not our flat plate collector. If it is a flat plate collector, whatever the incident solar radiations were there on the aperture area, same thing was passed on the flat plate collector absorber. So we didn't multiply with efficiency. But here if you see, all the solar radiations what is falling on the reflector surface, from that reflector surface, the radiations are taken to the receiver. I hope you are getting. So based on that optical efficiency, some losses will be there. How much is the loss given here? The loss given here is 25% is the loss because of the optical system. So all that radiation is not directly focused to the point. So some losses will be there. So to consider that losses, they have taken total solar radiation into efficiency. So that will be the effective solar radiation falling on the bottom side as well as top side of the point, of the focal point. Minus. So minus, as I told you, loss coefficient divided by concentration ratio you have to consider into bracket inlet temperature minus ambient temperature. So using this type of equation based on heat removal factor, one can find out the useful heat gain. So once you substitute all these values which are given in the problem, the useful heat gain by the oil is, you can just check here, 1,18,080 watts is the useful heat gain by the liquid flowing in this pipe or the receiver. Okay. Now you know the useful heat gain using FR value, or I can recall from this discussion, yesterday's discussion equation. This is the equation. Useful heat gain is area of the absorber plate into bracket S is the total incident solar radiation minus loss coefficient divided by concentration ratio and difference of temperature. So T mean they have taken, but for the FR value to consider, I have to take T inlet temperature. Okay, so T inlet minus TA. If you consider FR into TA area. Okay, the area of the system into FR is considered. That's why inside this bracket temperature, we need to consider inlet temperature minus T ambient. So this you can recall from the flat plate collector also. The only new terms are heat loss coefficient divided by concentration ratio into consider, and so total solar radiation which is incident on the absorber plate, which is very small. There we have to consider efficiency of the optical system. That is given 75%. Now useful heat gain is known, and we need to find out what is the outlet temperature of the fluid. So I'll multiply mCp delta T is equal to Q. So Q is known, mass is given 36 kg per minute. So I'll convert this into per second. 36 by 60. Cp value is given. What is Cp value? 3.2 kilojoules per kg. Given in SI units, no need to convert. Then T naught minus T inlet. T inlet is given 280. So this I'll find out the outlet temperature of fluid is 341.5 degrees centigrade. So this is in continuous movement. That's why the inlet temperature is more than the ambient temperature. So the cycle is repeating, and at this temperature, one can run a power plant. So like this, we are going to find out the different unknown things. So from next week, we'll start with solar economics. So today we have completed the solar concentrators. So maximum theory part is there with some few equations like this, so that you have to keep in mind. Okay. I'll stop the class here. Next class we'll start with solar economics. In the last part of